Hello, welcome to your lesson on integration of composites with linear functions. Let's begin with a starter problem. We have the derivative of a function given to you here, so we can see f primed. Our goal in part A is to find the original function. Well, we know integration is the reverse process of derivation, so if you integrate that, you should be able to bring that back to the original function. Let's try. All right, so again, we're taking the integral of that one, which will take us back to the original function. So the original function is the integral of this one. Therefore, we apply the rule, the power rule, right? We add 1 to this exponent and then divide by that new exponent or multiply by a fraction with that new exponent. And in the second one also, we add 1 to that exponent, so it becomes 2, and then multiply by that fraction. That simplifies into this. So now we have the original function. We know if this is the derivative, this is the original, because we took the integral. And B, it says, if the graph of the function f of x, so this original function, passes through this point, use this information to find the value of c. Because right now, when we take the indefinite integral, we always have this unknown c value. But now we're given a point on the original function. That point should allow us to solve for c. Try it now. All right, so basically we know that when x is 0, so the input is 0 into the original function, the output is 8. So 8 equals the original function with 0 put in for x. And if you solve that, these will cancel away, 0 and 0, and we're left with c must be 8. All right, so c is 8. So then give the exact equation for the original function. Well, it must be what we found it to be here, the integral of the derivative. There's that one, but now we know c is 8, so we can put it right here. So there's our original function. We did need that point, though, on the original function to do that. Otherwise, we'd be stuck with c. It's a special kind of problem for finding the actual equation. We're going to come back to one like that at the end of this lesson. However, let's do something else first. So we're going to recap the rules of integration you know so far. You have already learned how to find the integrals of x to the n, e to the x, and 1 over x. Those are the three main types of integration you've done. For x to the n, you've been using what's called the power rule, right? Where you add 1 to the exponent and then divide or multiply by a fraction with that new exponent. That's the basic rule of integration. We've also looked at e to the x and 1 over x, and we know the derivative of e to the x is e to the x. Therefore, the integral of e to the x is also e to the x. And then we looked at 1 over x as a special case, and that one, the integral is ln absolute value of x. So those are the kind of the three rules we know. What we're going to do today is consider these rules, these three rules, and find what happens when we have composites with linear functions for these three. These three rules, but what happens when we compose these functions with linear functions? Well, what does that mean? What does composition mean? Let's remind ourselves. So composition with a linear function. So here's a linear function we're going to call g of x, and we can see it's linear because it takes the form ax plus b, or like mx plus b. All right, so now we have this one, our basic power function, which we know the integral rule for, but we're going to compose it with this one. That means into this function, we're going to put the g of x function. So that g of x function goes into this one right here, and that means that x is replaced by the g of x function, which is that. So this linear portion has been inputted into this one. So we still have a power function with an n power, but now the base is this linear function. And we're going to see what happens when we do the integral of that. Okay, our other function that we've done integrals on is e to the x. Let's compose that one with a linear one as well. So we're going to take this h of x function, put the g of x linear one into it. That means this x is replaced by that linear function, and we end up with this. So again, there's our basic e to the power x, and now here's e to the power x, where there is a linear function within that. And the third one we know is 1 over x. And we are going, again, compose it with a linear one. So that linear function goes into this one. That means that x is replaced by the linear bit. And now instead of having just a basic 1 over x, we have a 1 over the linear function. So what happens when we do the integrals for those? That's our question for today. The integrals are a little different when we have those. Let's take a look. So first of all, let's begin here. Let's say you have this basic expression or function, and somebody says find d of dx. That means find the derivative of that. So try that now. What's the derivative of that? Finding the derivative of that, you're going to drop the 5 down, and then multiply, and then this goes down by 1, and we end up with x to the 4th. So that tells us that if we had to find the integral of x to the 4th, it would be that, right? Because if we took this and took the derivative, then if we went backwards and took the integral of that, should bring us back to that. So therefore, integral of that is that. And we know that. By our rules of integration, that works. We know that we add 1, make a 1/5 here. We know that rule already. So we've confirmed going backwards and forwards on this one. But what if we had this equation here, and you were told to find the derivative of that one? So try that. Find the derivative of that. Okay, here you'll need the chain rule. So again, the 5 drops down, we multiply here. This is decreased by 1. But then we also multiply by 2, because remember, when we have a function within a function, so we're doing chain rule, we have to take the derivative of the inner one, which is 2, and multiply by that. So now this simplifies a little bit. Those cancel, we have a 2 in front, we have this. So the reason we're doing these side by side is because now we can conclude if we had to take the integral of that, it would not equal this, the thing we started with. So basically we've shown that when we take the derivative of that, we get to a different place than this. And the reason we have that is because here we know the integral rule is add 1 here and then put the 1/5 in front, right? But here you might be tempted to do the same thing, saying add 1 here, make it a 5, and put a 1/5 in the front. So if we were following the same rules here, like the power rule, that we would say the integral is this. However, we have just confirmed by taking the derivative of this thing that it doesn't become this thing. So the power rule as we know it here, the simple power rule, does not work when we have this linear function within our power function. Okay, so that's what we're talking about. What happens when a linear function goes into that, is composed with it, and our basic power rule does not work. Okay, so let's continue from there. Let's see, let's look at it this way then. We just talked about that it looks like the chain rule. So let's talk about reversing the chain rule. Let's, for a moment, pretend that this is not an integral, that you were taking a derivative of this. What would be the chain rule, the steps of the chain rule if you're taking the derivative? Well, the steps would be this. First, you multiply by the exponent, right? The 4 goes in front, so we're multiplying by the exponent. Then you're subtracting 1 from that exponent, right? Becomes a 3. And then you multiply by the derivative of the inner function, which in this case would be 2. That's if we're doing the derivative. But since we're doing the integral, we're doing the reverse process. So let's think of it as the reverse chain rule. So we're going to do these steps in reverse order. The last step here was multiply by the derivative of the inner function. So now the first step here is going to be divide by the derivative of the inner function. So let's try that. We have this, and we're going to divide by the derivative of the inner function, so that linear function. So there's a 2 there, and we're going to multiply by 1/2, because that's like dividing by 2. Okay, then reversing chain rule again. Next step here is then add 1 to the exponent. Instead of subtracting 1, we add 1. So this is going to go up by 1 to 5. And the final step is, now that we have this new exponent, we are going to divide by the new exponent, which in other words means multiply by 1/5. So we've already done the add 5, multiply by 1/5, because that was our basic power rule. But now we have this extra bit of a half. That half is there because of the linear portion. So that's the thing that we're doing that's extra here. All right, that simplifies into 1/10, these multiply and that. Now, if you ran a derivative on that, it should bring us back to this. So let's check. So if you do this, your derivative would be multiplied by 5, so 5 would go in front, and then this would go down to 4, and then we'd also multiply by 2 because there's a 2 here, a derivative of that. So we'd have a 5 and a 2 out here, which means 10. Those 10s would cancel, and we'd have exactly back to that. Try the same process, the reverse chain rule on this one. Okay, so here's what you should have. You multiplied by 1/8 because of the linear portion. We're putting the 1/8 in front because of the linear thing. Then you upped this by 1 and multiplied by 1/4, our basic power rule. So here's our basic power rule, and here's this additional bit because of the linear part that's inside that function. That simplifies to this. And again, if you checked backwards, it would work out. You'd to do a derivative, you'd multiply by 4, multiply by 8 also, and that makes 32. Those cancel. This goes down by 1, and we have that. Try the last one. Okay, in C, again, reverse it. We have the inner part, and we have a -5 there, so we multiply by 1 over -5. And then for this part here, we raise the exponent and multiply by 1/10. So again, our basic power rule is the 1/10 and then this -1/5 takes care of the linear portion inside. Pretty easy rule once you get the hang of it. That simplifies to this. Okay, so now can you make a general rule then in this form? What is your general rule for these power functions that have a linear thing composed inside. Okay, check this out. Here's our rule, right? We raise that by 1, multiply by 1 over that. That's our basic power rule. And then because of the linear portion, we have that 1 over a in front. So again, there's our basic power rule, right, with the n plus 1 and the n plus 1 here. This matches that, except here, because of the linear portion, we have the extra multiplier in front. That's all. That's all there's to it. Okay, try the same thing for this one. We have our basic e to the x function, but now we have e to the power with a linear thing. All right, that's this. Again, the derivative of e to the x, sorry, integral of e to the x is just e to the x. But now because of the linear portion, we multiply by 1 over that value there. Again, the same as the power rule. So there's our basic integral of e to the x, and now because we have the linear portion, we need that extra multiplier with that fraction. Okay, try with this one here. This looks like 1 over x, right? So this one becomes like this, right? 1 over x, the integral would be ln x. So we have ln of that. And then again, because we have the linear portion, we put the extra multiplier with that value there. Okay, make sure you have those rules down. Here they are, all recapped in one slide. So write those down or think about them some more before trying these problems. So here's A and B. Try A first. Okay, check your work for A. Again, we raise this by 1, multiply by 1/7. Since we have the linear portion, we also have to multiply by 1/4, which we have here combined. Try B. Okay, B looks like a natural log. We see 1 over x format, but this is a linear thing. So again, ln of that, and multiply by 1/3 because of the linear thing. 2 more here. Try C. Okay, in C we have the e to the x function, but it has a linear piece. So bring out the 2, take the integral of that, multiply by 1/5 because we have the linear portion with the 5 in the front there, so 1/5. And there we have a simplified form. Try D. In D, that one might be a little trickier. It might look like a 1 over x in the beginning, but since we have this here, we cannot treat this like an ln x integral because we have a power here. Remember, our rule we just learned is only for compositions with a linear function, and 5x plus 2 to the 4th power is not linear, so we cannot turn this into an ln function. All right, that's important to know. But we can bring that up. Now that we've brought it up, we can apply the power rule. So the 4 goes up by 1. We divide by that value, and we have the linear portion, so we divide by that value as well. So there we have that one. And final, a few questions. We're going to come back to the same kind we started with, the kind where we find the original function, we don't know the c value. So here's a derivative function. It tells you a point on the original, right? It says when x is a half, y is 4. So find the integral of that. You'll have c in there, but then use this point to find out what c is. Okay, so there it is. We took the integral. We found this using our new rule with the linear portion. And then we don't know c, but we do know the point 1/2 and 4. So 1/2 goes in for x, 4 goes in for the y value. Solve it backwards for c, and then you can write your original function. Try B in the same way. It's the same kind of problem. Okay, in B, take the integral. You have it. Use what you have to find c, put it back into the function. These are a little tougher, so take a close look at your work there. Make sure you really understand the process here, because now we're using these new rules of integration and that whole idea of finding c. Okay, I think you're ready for the last question. This time it tells you there's a rate of change. A rate of change means it is a derivative, right? A derivative is like a slope or a rate of change. So we have a rate of change for a function equals this. That means if we took the integral of that, we would bring it back to the p function, the population function, right? Because this is a rate of population change. Integral would bring us back to just the population function. Okay, so check your work for that one. We took the integral. We found this function. Then we use the point that's given to us here in the information, plug it in, allows us to solve for c, and now we have that function there. And then now that you have that original function, it has you go even a step further here, which is you have the original function. Now tell us what the population is when t equals 4. So then you make that substitution and finish it off. All right, some tougher problems at the end there. Not so bad once you really put your mind to it. But I hope you did well, and we'll do more of that in class tomorrow. See you soon.